The sun, our nearest star. It is the source of life. Its energy fuels our planet. But the sun is not a quiet neighbor. It is a dynamic, active star. The sun's surface is a chaotic ballet of energy, which affects us here on Earth. Understanding this energy is crucial. We need to prepare for its potential impacts. The sun's activity follows cycles that influence the frequency of solar storms. These storms can be harmless or intensely disruptive. As we approach a peak in the sun's activity in 2025, we need to be aware of the potential for strong solar storms. We must understand the mechanisms behind these events and also be prepared for their possible consequences. The sun's surface is a sea of hot ionized gas called plasma. This plasma churns and bubbles due to intense magnetic fields. These fields create visible features on the sun's surface. Sunspots are dark, cooler regions caused by concentrated magnetic fields, which inhibit the flow of heat from the sun's interior. Sunspots often act as launch pads for more energetic events. Solar flares are sudden bursts of energy that release radiation across the electromagnetic spectrum. They are often associated with sunspots and are caused by the sudden release of magnetic energy. Solar prominences are arcs of plasma that extend outwards from the sun's surface, held in place by magnetic fields. Prominences can last for days or weeks and can erupt, releasing plasma into space. Among the sun's activities, coronal mass ejections, or CMEs, are the most significant for Earth. CMEs are massive bursts of plasma and magnetic field launched from the sun's corona, the outermost layer of its atmosphere. CMEs are often associated with solar flares or prominence eruptions and carry billions of tons of material traveling at speeds of millions of kilometers per hour. When a CME is directed towards Earth, it can trigger a geomagnetic storm, a disturbance in Earth's magnetic field. The severity of the storm depends on the CME's speed and magnetic configuration. The impact of a CME on Earth can be significant, disrupting our technology and everyday life. Understanding CMEs is crucial for predicting and mitigating their potential effects. The sun constantly emits a stream of charged particles called the solar wind. This wind flows outwards, carrying the sun's magnetic field into space. Earth is bathed in this solar wind. Fortunately, Earth has a natural defense mechanism. Our planet's magnetic field acts as a shield, deflecting most of the solar wind and protecting us from its harmful radiation. This magnetic field forms a protective bubble around Earth, called the magnetosphere. The magnetosphere deflects the solar wind like a rock diverting a river's flow. However, strong CMEs can compress the magnetosphere, allowing charged particles to penetrate our defenses. These particles interact with our atmosphere, causing various effects. Section 5. Impact on technology, power grids, and satellites at risk. Solar storms, particularly those triggered by coronal mass ejections or CMEs, can have a significant impact on our technology. One of the most vulnerable systems is the power grid. When charged particles from a CME enter Earth's atmosphere, they induce electric currents in conductors, including power lines. These currents can overload transformers and cause widespread blackouts. Satellites orbiting high above Earth are also at risk. CMEs can damage satellite electronics and disrupt their operations. This can affect communication, navigation, and weather forecasting. Protecting our technology from solar storms is crucial. Engineers are developing strategies to harden the power grid and safeguard satellites. These measures are essential for a technologically dependent society. Section 6. Disruptions in communication, GPS and radio blackout. Solar storms can disrupt various forms of communication. GPS systems, reliant on satellites, can experience inaccuracies or complete outages. This can affect navigation for aircraft, ships, and even smartphones. High-frequency radio communication used in aviation and emergency services is also vulnerable. The charged particles from CMEs can interfere with radio waves, causing blackouts. These disruptions can have serious consequences. Air traffic control can be hampered, leading to delays or grounding of flights. Emergency responders may struggle to communicate during critical situations. Understanding the impact of solar storms on communication is crucial. Developing backup systems and alternative communication methods is essential to mitigate these disruptions. Section 7. Aurora Borealis, the beautiful side of solar storms. While solar storms can have disruptive effects, they also produce a stunning phenomenon. the aurora borealis, or northern lights. This spectacle of colorful lights dancing across the night sky is a visual reminder of the sun's power. The aurora occurs when charged particles from the solar wind collide with atoms in Earth's atmosphere. These collisions excite the atoms, causing them to emit light at different wavelengths. The colors of the aurora depend on the type of atoms involved and the altitude of the collision. Oxygen produces green and red light, while nitrogen emits blue and purple hues. The aurora is most commonly seen at high latitudes, near Earth's magnetic poles. During intense solar storms, the aurora can be visible at lower latitudes, offering a rare and breathtaking display. Section 8. Historical solar storms. Lessons from the past. Throughout history, Earth has experienced numerous solar storms. Some of these events have had significant impacts, providing valuable lessons about the sun's power. In 1859, the Carrington event, the most intense geomagnetic storm ever recorded, disrupted telegraph systems worldwide. Telegraph operators reported sparks flying from their equipment, causing fires. In 1989, a solar storm caused a major blackout in Quebec, Canada, leaving millions without power for hours. This event highlighted the vulnerability of power grids to solar activity. These historical events demonstrate the potential consequences of solar storms. Studying these past occurrences helps scientists understand the mechanisms of solar activity and develop strategies for mitigation. Section 9. Preparedness and mitigation, facing the solar threat. As we approach the solar maximum in 2025, preparedness and mitigation strategies are crucial. Scientists are actively monitoring the sun, using sophisticated instruments to track solar activity and predict potential storms. Space weather forecasting centers, like the National Oceanic and Atmospheric Administration Space Weather Prediction Center, issue alerts and warnings about upcoming solar storms. This information helps governments and organizations prepare for potential disruptions. Strengthening the power grid is a priority. Utilities are implementing measures to protect transformers and improve grid resilience. Developing backup systems and alternative energy sources is also crucial. Satellite operators are working to harden their spacecraft against the effects of solar radiation. Developing strategies for redundant communication systems is essential to mitigate disruptions in navigation and communication. Section 10. Conclusion. Monitoring and understanding for a safer future. The sun, our life-giving star, is also a source of potential threats. Solar storms can disrupt our technology, communication, and everyday life. Awareness, preparedness, and scientific understanding are our best defenses. Continuous monitoring of solar activity is essential. Space weather forecasting provides valuable information about upcoming storms, allowing us to take necessary precautions. Investing in resilient infrastructure, developing mitigation strategies, and fostering international collaboration are crucial steps in facing the solar threat. By understanding the sun's dynamic nature and preparing for its potential impacts, we can harness its energy while mitigating its risks, ensuring a safer and more sustainable future for humanity.